Well, hello everyone out there, and welcome back to yet another video on this autograd series from scratch. So you know that we've just built the computational graph for our forward pass, and we were just working on this backward pass backpropagation implementation. And guess what? Successfully, I have done it for half of the network, and half of the network I mean that I've used it for like tensor mean squared error and for LayerNorm operations, right? So we are just verifying for each single node, a tensor node that has its own metadata, that has its own parents linkage information and its own backward function information. So there's a lot into it, right? So without any further delay, I'm going to show you the computational graph, which I've already shown you in the previous videos as well. In case you haven't seen, go watch out that one. So that you can have an idea that how things are working underneath, right? So without any further delay, I'm going to open this graph, and this is it. This is it. So what we have is we have all the nodes. So let me just tell you something. So I've zoomed in a bit over here. So you see this in this main red block consisting of sub blocks, right? This main red block is basically a tensor consisting of metadata associated with it. So I'm only printing like three different values, three different parameters of this metadata. It has got lots of different ones, like parents information, like operations information, like number of parents, like stride, shape, dimensions, and data, gradient data, everything. So for the sake of simplicity, I've just printed three different parameters over here. So starting from here, this is actually our final so you see we have tensor ID, we have tensor operation, we have gradient. And since this video is basically on backpropagation, so that's I'll be emphasizing on gradient. So in case you want to see how we build this computational graph, you can check out my previous videos. And also guys, make sure to like and subscribe to our channel, because I can see there are lots of different people who are watching our channel but they're not subscribing. So you see I always see like 95%, 90% new users, and I want you to subscribe as well for more such kind of videos, right? So back to our topic. So here's the gradient, right? So we have computed this gradient only applying some final function on our final operation. And what does that mean? So let me just open a file called tensor so that I can tell you that how have I originated this graph. So you see this is our final loss, right? And final loss after LayerNorm, what it does basically, and let me tell you one thing, I'm currently applying for only two layers, that is mean squared error and LayerNorm. So we'll be verifying if things are working fine, then we'll be going for the deeper layers like multi-headed, which has lots of different tensor slice operation, concatenation, difficult sort of operations, and then we sort of will be applying for neural networks and everything, and that's how we will cover the entire graph, right? So I'm a strict believer of first verify your small parts so that you don't have to be you don't have to chase the bugs all the time in a big update, right? So you see this is our LayerNorm forward method, and after that I've applied some loss function, and for now this loss is considered this as a sum operation. So it takes all the values of a tensor and is sum them and creates a one scalar tensor, and scalar tensor I mean by one value, right? And then this is actually the entry point, and by entry point mean that at some point, at some final stage, we have to first manually update the loss gradient, which is with respect to its own self. So d loss by d loss going to be 1. So that's the first value that we calculate manually. Rest of everything is updated using automatic gradients. So that's why we call it autograd, because it automatically upgrades the gradient values using chain rule, and just depending upon the tensor node how it has actually created and what are the parents involved in the creation, and then it just calls the backward functions, and it just calculates the gradient, right? So this is actually the entry point of ours. We set the gradient 1 with respect to its own self is going to be 1, and then we traverse backwards, right, using topological sort. And by topological sort we mean that it just makes sure that parent children's are visited first before the grandchildren's, right? In simple words, that's the hierarchy. That's how I can explain it, right? In DFS, what happens is it takes one branch and it goes all the way down to every single children, and then it comes backward and visits the other children's, not grandchildren. So what happens in topological sort is just it ensures the children's are visited before the grandchildren's, or if you're going in that way, like from top to bottom. Okay, but in case of backward we have reverse, right? So in case of reverse, you can see that grandchildren, and then it just Yeah, so in case of backward also, it just first traverses the graph, stores everything in topological list, makes the orders of the children's, and then update the gradients likewise. So first of all, we have the gradient for this loss, which is 1, and then this loss is transferred to the other operations, operation add and operation add, further transfers this gradient to two different tensors which were involved in its creation. So operation, sum is very simple. So if you take two tensors and like a plus b equals z, and derivative of z with respect to a is going to be 1, and derivative of b with respect to z also be going to 1. So, and you multiply 1 by the previous gradient, it's going to be always the previous gradient. So upstream gradient times 1 is going to be upstream gradient. So for now, we have upstream gradient equals 1. That's why 1 is transformed over here. Very simple. Whatever comes from the previous node will be transferred smoothly to the other nodes, right? So sum is very simple, and subtract is like exactly opposite. This subtractive term will take the negative sign. Instead of adding them, we'll subtract the value, right? It's very simple. And next we have, you see, so we have different kind of operations, like operation expand rows, operation element wise product, we have operation expand rows, divisions, and that's how we are maintaining. So we're going backwards using chain rule, using derivative, using previous derivative and local derivative, and something previous derivative is like we're caching the gradient at every single point. So this cached gradient is called previous gradient or upstream gradient, right? And we're using that upstream gradients with local gradients to find, using chain rule to update the rest of the gradients, right? And yeah, guess what, we have error over here. So you see the difference. We have red blocks, red rectangles, and this is a black rectangle, and the reason it's black is it's not updating any gradients. We have 0 gradient, and we need to figure out what exactly is wrong with the tensor square root operation, right? So gradient of a square root, if you take the square root x to the power 1 by 2 and you take the gradient with respect to x, is going to be like dz with respect to x is going to be 1 by 2 x raised to power negative 1 by 2 derivative of x, and you take the x power negative 1 by 2 to down, that will make positive, so you'll have 1 by 2 under the root of x, right? This will be the gradient of x raised to power minus 1 by 2, right? So there's something wrong. I mean, something wrong with the implementation. That's why we have gradient. We'll need to check this out. And also you see this operation add, so fill like, operation whenever you want to fill some tensor with some value, some float value is just called fill like, and it has its own back method which calculates its gradient, right? And this is operation expand columns. So operation means, so we are getting the tensor gradients smoothly over here. And now the point is, there's one mistake over here, which is right, which is here, and we need to figure this out, what exactly is wrong with this gradient. And also we need to verify these gradients, whether they're calculated correctly or not, using a method called manual gradient, or what, I don't exactly remember the name of that gradient. It's something called f dash of x is equals f of x plus or minus f of x plus h divided by f of x, right? So this is actually the equation which put the values, and h is basically a small value that you bump into the x function, and you just divide it with the existing value, f of x minus f of x plus h divided by f of x. So that's how you can actually verify excuse me, if your gradients are working. So now you guessed it, right? So we're at this stage that we have successfully built, first of all, arena, custom memory allocators. Then we built all the layers, like tensor forward pass, for forward pass multi-head attention, phi4 neural networks. We created tensor abstract. We created a whole tensor library consisting of each and every single method, just like PyTorch. And we have built a computational graph. We have built directed acyclic graph. We have traversed that graph, and now we are just building on this very final part, which is actually the updating of the gradients, right? So if this works, this is going to be a huge success with this runtime, and then I'll be leaving this project, and we'll be working on collaborating with llama.cpp and GZML, which is basically a tensor library for deep learning in C, which is actually another exciting project. I have lots of different thoughts going on. Maybe I keep on working on this framework to make it full-fledged Python interface and data loaders and stuff like that framework in which you can use Python and you just can pass the data, and there will be only three methods like load data, pre-process data, four methods, forward pass and backward pass, and that's it, right? It's going to be that simple, inshallah. So keep supporting my channel, and if you haven't liked, subscribe already, please consider subscribing for more such kind of videos, and I'll see you in the next video. Take care. Bye.